Please, Ranger.
Okay, well, thank you for having me here. Next year, when are we going to do it again? All right, we plan for the future. So this is going to be a bit of a change from the talks, but it's connected. I'm going to tell you some work about liquid crystals that I've done with a bunch of people. Helen is my former student. She's at Northwestern now. Tom Machon is Gareth's former student. He's at Bristol now. And Brooke Hawking is Tom's former student. I don't know where he is now. Okay, so this is a crystal, all right? And a crystal, right, has these dots. This is a picture from Peierls from a long time ago. And what's the deal about crystals? Crystals, you know, we think of these regularly ordered things, but then, you know, you can shear a crystal, you can tear a crystal. And somebody said, oh, but you know, there's like a mole, like 10 to the 23rd atoms, right, in a piece of crystal. And if there's all these chemical bonds you have to break to move a crystal surface over itself when you shear it, how is that possible? The amount of force and the amount of energy you'd have to give, the amount of energy that you'd have to give is huge. So how does it move? So I like to think of it like this. So compact shelving. Now it's true that if you're very strong or very naive, you could go to this end and start cranking and try to get all 5 shelves to move, right? And sometimes it's even more than 5 shelves. There's 20 shelves. And if you do it, you can work really hard. You can get your friend to help you. But it's much easier to move it 1 shelf at a time, right? Or maybe 2 shelves if you're strong, right? But you can move them 1 shelf at a time. And this is exactly how a crystal shears over itself. So here's a picture of a crystal doing it. Instead of having this entire plane, the slip plane, move all at once, it moves 1 atom at a time. So even though in the end you've spent the same amount of energy, the force is much smaller because you're only moving the force, you're only giving enough force to move 1 row at a time. And it takes a little longer, but that's how crystals move. And this was a puzzle when they started thinking about crystals. How can you shear crystals? It seems like they'd be infinitely strong, but it's because they have these defects. And the defect is in how the things are packed. You can see very clearly that at the bottom there are 7 rows or 7 columns, but at the top there are 8 columns. Okay. So I know this is under the auspices of math, so I'm going to prove a theorem for you. All right, this is the only theorem I'm going to prove, right? Which the fundamental theorem of algebra. Okay, and every polynomial has a root in the complex plane, and you start with a polynomial like so, right? And then you say, okay, here's my big polynomial, and I assume it has no roots. Assume there are no zeros. And then I can form this new function, which is just a phase, right? A unit phase, and it's defined everywhere because the numerator never vanishes, so it's not a problem. And you choose a circle that's really, really big, so big that this term dominates everything. And you say, out on that circle, if I look at this function p, it winds by the phase winds by 2 pi n as I go around, and then what I can imagine doing is I can imagine shrinking the circle, right? And since there are no roots in here, I never pass anything. This function stays perfectly well defined. I shrink the circle. I can get the winding as a function of r until it shrinks to a point. And when it shrinks to a point, clearly the phase doesn't wind at all, right? I go around a little point where it's constant. And so on the big circle, it winds by 2 pi n. On a little circle, the winding 0. This is a contradiction. It means that there's a root inside. The same is true with liquid crystals, all right? If you do some calculation and do some measurement far away, it means there's a problem on the inside, all right? So we have topology where we count things on the outside, but just like the fundamental theorem of algebra, it also tells you about something on the inside, right? So if you looked at the monodromy of a function out at infinity, and you said, oh, it has monodromy that isn't 0, you know there's a root inside. I'll give you another example of it. It's my favorite example. No, it's not my favorite. It's a good example, okay? So some people like to talk about the integer quantum Hall effect. you have a Hamiltonian, which is a two-state Hamiltonian. So these are just 2 by 2 matrices. This is the identity. It's boring. These are the Pauli matrices. And there's 3 of them. So there's a vector out in front, D. And it depends on what wave vector you're on, right? So it depends on K. And if D isn't 0, then you can construct a unit vector, which is D over its magnitude. If D never vanishes, then you can construct this unit vector. You have a map from the Brillouin zone, which is this torus in K space, to the unit sphere. Here's the unit sphere. Here's the map, N. You can calculate this, the pullback of the area swept out on the sphere. And this has to be an integer, right? So suppose you take some material where this charge is 1. And then you put it next to a material where the charge is 0. For instance, the charge would be 0 if D always pointed in one direction. If you just had a simple gap system, right? 2 states that are always constant. So you put these 2 things in contact with each other. How can you have Q equals 1 next to Q equals 0? As you move smoothly from this side to this side, this whole integral can't change continuously because it's an integer. So what does that mean? It means that on this boundary, something must happen. And what must happen? It must be that you can't define n. The only thing that's missing. I was assuming that D wasn't 0. Since I can't define n, it must mean that D isn't 0. And it means there's a place where D vanishes. When D vanishes, it means that you have 2 states with the same energy, because all you have is the identity. And that means that there's no gap, and you conduct electrons freely across this boundary. Those are the edge modes, right? So again, you can use topology to tell you that there's some number in there. And this is an important idea, that when you have 2 states that are separated by a different charge, a different topological charge, there can be on the edge, on the boundary between them, a special low energy mode. The gap closes. Okay, no gap. So it's a diverse audience. Let me remind you or tell you about liquid crystals. Liquid crystals are the ultimate generalization of liquids and crystals. They go in between. A liquid crystal, usually you think of it as a material made out of anisotropic rods. And in the isotropic phase, the molecules are pointed randomly, and their centers are located randomly. So this system is homogeneous and it's isotropic, right? It enjoys all the symmetries of the Euclidean group in 3 dimensions. But then you concentrate the system or you reduce the temperature and boom, you get the nematic phase. The nematic phase is special. It is still homogeneous. It still is translationally invariant, but all the molecules point in the same direction, okay? And so it's ordered, but it's not so ordered as a crystal. Right? A crystal, you also know the positions, right? It's not that ordered. It's only kind of a little ordered. The orientation is ordered, but not the translations, okay? And you can make ones out of disks. And then I'm going to be eventually talking about this phase, the Smectic phase, which is kind of an in-between. It has molecules. They form layers. The layers are evenly spaced, but in the layers, they're completely fluid. It's like people walking around in different floors of a building, right? Their vertical distances are kind of set, but the horizontal, in the plane of the building, they're just a fluid. And they all stand up straight. Their heads point to the normal to the surface. There are more exotic ones where everybody's tilted over, okay, or people are twisting, but I'm not going to talk about those. I just did, okay. So this is what it looks like, though, when you look at liquid crystals. This is the nematic phase. These are the lines, the NEMA. Okay, here's another phase made of liquid DNA. These are real pictures. These are real pictures without color enhancement, right? Here's a cholesteric phase. It kind of looks like a brain, right? I'm trying to tempt you to learn more about liquid crystals. This is called the blue phase. Good name, right? And the blue phase, even though this looks like it's a crystal, is not a crystal, right? It is something where every point in space, there's a 3-dimensional orientation of molecules, but they are not positionally ordered, or they don't have to be. And this is a Smectic phase, and we'll talk about that. Just so you know what we're doing, and you can see how topology comes in. here's a picture of a liquid crystal, a nematic again. And what are you looking at? What you're looking at is, well, I'll tell you a second. What you see when you look at the nematic is you see these places where there are 4 black lines coming together. And sometimes you see 2 black lines coming together. What are you doing? There's a backlight. There's a polarizer and another polarizer, which I'll call the analyzer to distinguish it from the polarizer. They're at 90 degrees. Since they're at 90 degrees, if you send light through, regular light through, you get black. But the molecules on the inside, these liquid crystal molecules, are not only anisotropic mechanically, they're also anisotropic optically. So light that travels parallel to the axis goes at a different speed than light that travels perpendicular to the long axis. And so you take the light, it comes in the polarizer, it decomposes into this new frame set by the liquid crystal. And then the 2 different modes, the 2 different pieces, move, but they move across the sample at different rates. And when they come back on the other end, one is lagging the other. And so it turns out you go from having linearly polarized light to elliptically polarized light. And then some light gets through. When do you see black? You see black whenever the molecules happen to be along the polarizer direction or the analyzer direction. Okay, and when that happens, you get black. So these black lines are the pre-images of the direction polarizer and analyzer. Okay. And what do you see? Why do you see 4? Because if you have a defect of some kind, a swirly kind of defect, and you say, oh, well, it's black wherever the polarizer, wherever the molecules are parallel to the polarizer or the analyzer, you get 4 brushes. Why 4? Because you go through the polarizer once and the analyzer once and the polarizer once and the analyzer once. So there are 4 brushes as you go around by 2 pi. Ha-ha! Here's the great part. See? 2. How do you get 2? If there's only 2 brushes, it means you go around the polarizer direction and the analyzer direction. Only one. Polarizer, analyzer, and you're back to where you started. These phases actually have an extra rotational symmetry, a Z2 symmetry. You can turn all the molecules over. You can rotate them by pi, and it's exactly the same. So drawing them as symmetric ellipsoids was actually correct. They're not vectors, right? These aren't arrows pointing in any direction. This is crucial. This is crucial, and this is how it's different than everything we've been talking about, or everything we've been talking about so far. Okay. Now, let me go back. When you look at these defects, one thing that you might notice is that when there's 4 brushes coming out, or 2, you don't know whether it's going around clockwise or counterclockwise, right? You still get 4 brushes. How can you decide? Well, you can do an experiment. You could start here and you see 4 brushes. So it's plus or minus 2 pi, plus or minus 2 pi. But you guys are, you guys know, far away there are no brushes. So in fact, there's no charge, right? There's no winding. These must be opposite winding. And you can do a small experiment to see that they're opposite winding. It'll get there. And it all disappears. So this is under the same picture. This is the same setup. And you're watching the dynamics. So by watching the dynamics, you can decide what the charges are. Without that, you have to watch them forever. You have to watch them be born, and then you have to watch them forever. And that's always difficult. And that's the difference. That's also an important difference. Okay. So back to the crystal. What do I mean by a crystal? So we can think of a crystal this way. You go outside. There's the beautifully tiled streets. There's dots on the floor, right? And here are the dots. But that's not how we think of crystals, right? Bragg told us a long time ago, crystals are actually sets of planes, the Bragg planes, from which we scatter X-rays, for instance. And so here's a set of planes, and here's a set of planes. And these planes, the red planes and the blue planes, are basically equally spaced, even though there's a defect here. A dislocation, there's a place where there's an extra red line, right? But still, this is, this is just one little point in a giant sea. And the spacing more or less is the same. So what will happen is if you do X-ray scattering, you will get X-ray peaks they will scatter, they'll diffract off of these planes, and you'll get peaks that tell you that there's an average spacing in the red direction and average spacing in the blue direction. So we should think of a crystal not as a bunch of points, but as a density wave, or in this case, two density waves intersecting. Okay, so I want to do a simpler case. I'm going to start with a Smectic. You'll see why. So here is the crystal. Let me ignore the blue planes for a second. And let me think about just a Smectic. Remember I told you about Smectics? They don't have any periodicity in this x direction, only in the z direction. And this is a dislocation. In some places, it's like here. You see, oh, I don't know why I'm pointing to it in my pointer. That thing in the middle, that's like the mezzanine, right? We're in Europe. This is 0. Up there is 1, and that's the mezzanine, okay? And you see the mezzanine doesn't make it all across because that would be crazy. Then people in the mezzanine couldn't see anything. So here it is. And there's an extra layer, okay? And so here's the extra layer. And you have this extra layer, and you say, oh, well, okay, that just looks like a place where there's an extra layer, a dislocation, just like this. But here's the thing about crystals that's different or important. Crystals, these black lines, they're not just constant phase or something. They're places where there's stuff. So there's a density wave. That means there's stuff on these black lines. There's a density wave. This is the maximum of the density. And you all know that between two maxima, there are always minima. And so, in fact, I can draw the maxima lines, the black lines, but there are the blue lines also, which are the minima. There are minima and maxima in crystals. There's where the crystal is and where the atoms are and where the atoms aren't. And if you like probability, these are where the atoms are most likely to be, and these are where the atoms least likely to be. Okay? And this is how you do it. You say, here's the Smectic density, rho of x. It has a background density. It has a order parameter. When delta rho is 0, the Smectic has constant uniform density. When delta rho isn't 0, you get a modulation, where phi is some phase field that tells you which layer you're on. Level sets of phi equals 0, phi equals 2 pi, phi equals 4 pi. Those are the maxima. And phi equals, pi and 3 pi and all that. Those are the minima lines. And what you see is that you look at the defect here, in particular, look at this one. Look at this one on the minimum. This is a place where, in fact, the layer normal, the direction normal to the minimum layers, rotates around by pi, backwards. Right? It goes, right? Was that clear? Okay. And actually, this is a place where it rotates by pi counterclockwise, right? You see, liquid crystals can do this because they have that up-down symmetry. Remember I showed you with that picture? So liquid crystals, because they have this Z2, this extra Z2 symmetry, they can actually enjoy defects that look like this. These are defects not in the density wave. These are defects in the orientation of the planes, right? Or in this case, just lines. You can see this a number of ways. For instance, phi and phi plus 2 pi, those give you the same density wave. That's the translations. And then there's phi goes to minus phi, and that's the flip. And so, in fact, you can only determine phi up to a 2 pi and up to a sine. Okay. Where does delta rho come from? Delta rho comes from some Landau theory. All right, in this Landau theory, there's some sort of energy, some phenomenological free energy, where there's a quartic term in delta rho, a quadratic term, and the quadratic term changes sign. And when it becomes negative, delta rho wants to not be 0. That tells you that there's a crystal. Below some temperature, there's a crystal. Above some temperature, there isn't a crystal. Okay? And the important thing is that delta rho is what tells you if you have a crystal or not. Notice that in this picture, if I weren't worried, if I didn't talk about the density, and if I just said that these were phase fronts, like in optics, if they were just phase fronts, you'd say to me, oh, well, there must be a place here, there must be a 0 in the complex scalar associated with the phase front, right? Just like what DeWitt was talking about, just like Mark was talking about, right? If I wrote psi as e to the I phi, then there'd have to be a 0 here. But I don't have to have a 0. I actually have delta rho defined everywhere. And the way I do it is by limiting where these disclinations sit. Let me explain that to you. Okay? So here is the manifold of possible ground states of the smectic. So you can take a smectic and you can translate it by 2 pi, and you can rotate it by pi, and they give you exactly the same thing. And all of these are the different ground states. The ground states where they're pointing like this, and the ground states where they're pointing like that, and the ground states where they're higher, and the ground states where they're taller. But you see, translating and rotating is not the same as rotating and translating. Right? If you translate and rotate, it's like translating backwards. So when I look at the translation, when I look at the rotations, everything's fine. Right? But the translations have this twist in them. So in fact, the ground state manifold's a Klein bottle. It's very exciting, right? Something pointed out, at least to me, by Hans Reiner Trebin. And the Klein bottle is what makes this interesting. And it's because of this shift by pi, or this rotation by pi, that we're going to get something. Generally speaking, the way you talk about defects in materials is you say, here's your sample. Here are defects. Those are the places where there must be some 0 or some singularity that we can determine by doing some measurement far away from the defect. You do some measurement far away, and it corresponds to some non-contractible loop in the ground state manifold. For instance, here, this is the Klein bottle. Okay. Okay, that's, you know. Now, smectics are a little complicated. There's this theorem that Poe proved quite some time ago. That says if you have systems that are layered, like this, like a smectic, they can't have any kind of disclination that they want. There can't be any kind of singularity. There can be one where they wrap around like in a bullseye, where the normal wraps by 2 pi, here the normal wraps by pi, here the normal doesn't do anything, minus pi, minus 2 pi, minus 3 pi. But the theorem says you can't go beyond +1. You can't go beyond +2 pi. The only way to go beyond +2 pi is to squish all the layers together, right? These are so-called measured foliations, okay? And these if it's a measured foliation, which a smectic is, you can't go this way. But you can go as negative as you like. It's not true in the nematic. It's not true in these optical phase fields. In principle, you can have any charge you like, positive or negative. But already, smectics give you something that's a little different. Now let me go back to my smectic, and let me draw the ground state manifold again. I worked with a bunch of British people who have some sort of orientation thing, you know, left and right, and so the axes are changed. Now the horizontal axis is the shift, and the vertical axis is the rotation. But that's okay. The picture on the left is movement across the ground state manifold on this contour gamma. It's a closed curve. It goes from here to here. But notice, what does it do? It changes the shift by 2 pi. That would be a dislocation. This would be a place where you go around some loop and you come back on a different floor, like when we go up a spiral staircase, or when you go around on the mezzanine. If there were another set of stairs, you could go up. You could go up 2 floors to the top, 2 up, and then 1 down, and then 2 down, and you'd end up in the basement. You know what I'm saying? Right? Right? You don't know how the floors are connected. But you know, you can take this path and deform it. You can have it start here, go straight down, go across, go straight up, go across, go straight down. It ends and begins at the same place. But notice now that the shift in phi here cancels the shift in phi here. Because even though the red curve is still pointing the same way, you now measure distances backwards. So in fact, this is a configuration where there's no shifting. There's no place where you don't know the value of phi, right? Because phi is unchanged. And you can replace this line with 2 lines that just go on these 2 curves. Why can't I put these curves anywhere? Why did I have to choose phi equals 0 or phi equals pi? Because those are the fixed points, right? Those are the fixed points. If I went from phi equals pi over 2 and went straight up, I would get to phi equals 3 pi over 2 mod 2 pi, right? Or phi equals minus pi over 2 mod 2 pi, whatever you like. So this isn't the closed loop. Closed loop, a line that starts here has to end here. And then there's a shift in phi. Then you're changing in the phi direction. But if instead you restrict yourselves to these fixed point lines, phi equals 0 or phi equals pi, then you have no problem. And phi equals 0 and phi equals 2 pi are the same. So what you do is you take this dislocation, which would make you think that delta rho had to vanish because you can't define the phase there, and you break it into two disclinations that sit on the minima and the maxima. So if you sit on the minima and the maxima, you don't have to melt the crystal. Okay? And the optical fields and phase fields, they don't enjoy this extra symmetry. Right? But crystals do. Okay. Now, just a little bit of thought would tell you now if you have a dislocation, so any place where you add a layer, there's no way to build a dislocation without having a charge plus 1/2 disclination. Maybe one disclination is on a minimum and one's on a maximum. That's not my problem. All right, the minimum and the maximum are perfectly well defined. And then you say, how is it possible to move a disclination? This is called disclination glide, or dislocation. How do dislocations move up and down in a sample? And the answer is you have to melt the smectic, because in order to move a dislocation up, if I want to move it up one layer or down one layer, sort of like, you know, you have a bump in the carpet and you kind of move them over slowly, just like the original movie of Moving the Books, or Peierls' movement of the dislocation lines. How do you move the dislocations over? How do you do what Peierls did? To do it, you have to take one of these disclinations and it has to move off the minimum or the maximum. Once it does that, you can't define delta rho, and it means the crystal melts. Why is delta rho not 0? Because that's the low energy state. So you actually have to melt the crystal, which costs energy. And this is called the Peierls-Nabarro barrier, that to move a dislocation, it has to move through. And you could say it's because of periodicity, that there's a periodic potential, but the potential is coming all from this topological construction. All right? Okay. So this just summarizes what I said, right? The zero energy locations of dislocation is determined by topology, and the only way to move a dislocation is you have to melt delta rho. You have to make delta rho 0. You are now not in the crystal state. If you want to stay in the perfect crystal, then the dislocations are frozen, and they have to melt to move on. This is just like the quantum Hall effect, all right? In order to change from one charge to another charge, you have to melt in the middle. The gap has to go to 0, which is not happy. The thing doesn't like to have a 0 gap, just like we're not happy to have delta rho v0. Okay. How do we do this for crystals? Well, in crystals, 2D crystals, it's easy. Instead of saying that there's one density wave, there are two density waves. Phi 1 and phi 2 are two phases. You parameterize the phases in terms of some reciprocal lattice vector. Those are the things that tell you which direction to move, .x, and then there's an offset. So you can move them up and down, and these tell you the orientations of how these are. The G's do not have to be orthogonal to each other. They can be oblique. They can be at funny angles. And for instance, let me imagine that I have a square lattice like I drew here. So in a square lattice, there's a density wave. It's just cosine x plus cosine y. Where are the atoms? They're at the double maxima. Right? So, oops, okay. So imagine that I rotate the system. I have the angle theta, which tells me the orientation of the crystal, and I have these two offset functions, phi 1 and phi 2, and I rotate the crystal around the origin. Well, what happens? Theta, when theta changes by pi over 2, it's a square lattice. It's a square lattice, right? So nothing changes. So you can rotate. However, when you do the rotation, phi1 becomes phi2, and phi2 becomes minus phi1, because you rotated by pi on 2. But these, just like I told you that there were the symmetries of the Smectic, this is the symmetry of a square lattice, right? This is the symmetry of a rectangular lattice. In a rectangular lattice, you have two vectors that are perpendicular to each other, but they're not the same length. And so now you can't rotate by pi on 2. You can only rotate by pi, right? But there are the symmetries, and it changes both the values of phi. And so now you look for the fixed points of these, where the phis are only defined mod 2 pi, right? And when you look at the fixed points, first I'm going to draw the ground state manifold for you. Here's the square lattice ground state manifold. I have the two variables phi1 and phi2, the two offsets. Here's the rotation by pi over 2, and I glue the top square to the bottom square, right? So it looks like this. In the rectangular case, or an oblique case, where G1 and G2 are just arbitrary, right, don't have any special relation, then you actually have to rotate it by a whole pi here out, so it's more twisty. In a triangular lattice, which I'll mention, in a triangular lattice, there have to be 3 phase fields to make the density wave threefold symmetric, but one of them is the sum of the other 2. So there aren't 3 independent phase fields. And you discover that you do a rotation by 2 pi on 6 in a triangular lattice, and it connects the bottom hexagon to the top hexagon. These different lines are different fixed points. You notice that the triangular lattice only has one fixed point in the middle. In a moment, you'll tell the difference between the green, blue, and the red ones. Okay. What's the difference between the green, blue, and the red ones? Here's the triangular lattice. Okay. The triangular lattice, well, they're just different. They're different places on the lattice. On the triangular lattice, if you do a rotation by pi on 3, 2 pi on 6, the fixed point has to be at the origin. What do I mean by the origin? It has to be at a double maximum. Okay? In a square lattice, the fixed points are double maxima or double minima. So again, the disclinations have to sit either at double maxima or double minima. And then finally, oops, darn. Okay. In the rectangular, oblique, or centered rectangular, the disclinations can sit actually in these mixed places, double maxima, double minima, or mixed ones. Okay, and those are just the different fixed points that you can find for these symmetries. And so let me show you an example. Here's a triangular lattice, right? Everybody shows you this triangular lattice, right? And here's a triangular lattice, and you see there's an extra layer. How would you see that? There's a dislocation. You start here, you walk 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and you don't end up where you started, right? But you can see what this is made of. This is made of a place here where there's a disclination, where there are 7 neighbors to this point and 5 neighbors here. But I already told you that. Okay, there's the 7, there's the 5. They have to sit at double maxima. The phase disclinations that I'm talking about have to sit actually on where the lattice points are. This is the only way you can do it. But what about a square lattice? The square lattice is more funky because when you draw a dislocation in a square lattice, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Sorry. 0, 1, 2, 3, 0, 1, 2, 3, right? You guys like 0, okay? So there's a dislocation. Here's the place where there's something that has only 3 neighbors. Where's the other one? Well, there's the one with 3. That's at a double maximum. And there's the one at the double minimum. The double minimum of what? Well, right, there are the minima of the density also. And that's where it's sitting. Okay? And let me point out to you that even though these two charges are opposite sign, right, one rotates around by an extra pi, one rotates around by a plus pi over 2 minus pi over 2, which based on the movie I showed you, they should collapse and disappear. They can't. because the maximum and the minimum can't be the same place without melting the crystal. So here's a structure which is very happy, and these two disclinations, even though they're opposite charge, are forced to sit there. They can't get any closer. They're topologically constrained. So are these. Okay. Sometimes the phase disclinations correspond to geometric disclinations. I don't know why this isn't there yet. I'll draw. Okay. Now, I've been telling you about edge defects, and I've been doing everything in 2 dimensions. Right, so here's a 2-dimensional version, a 3-dimensional version where you add this extra layer. But there are other kinds of dislocations, screw dislocations, which are kind of what happens in optical phase fields. What did you call this, Mark? Orbital angular momentum? He called it a helicoidal phase field. He called it Dennis's helicoidal phase field. Here's a screw dislocation. This is what happens when you walk up a spiral staircase. Here's the density wave. If I just think about dislocations and I just think about these as, say, wave fronts, well, then what you'd say is, in both cases, when you integrate phi around a closed curve that encircles the defect, you just get some number that's 2 pi times an integer, right? Either, you can go up, or you can add an extra layer, or you can just go up a layer. Well, from the point of view of phase fields, these two are the same topologically. There's no distinction. But I'm going to convince you they're totally different for in a smectic. Okay. Smectics, crystals have screw dislocations, right? Which you can imagine. You build this thing a stairway. You can see real pictures. This is a real picture of a real set of screw dislocations coming out of a surface. In fact, this is how surfaces grow. Instead of growing a whole layer at a time, they grow and they sweep out an edge dislocation that goes around, the so-called Frank-Reed source. Let me back up. Let me tell you about a different topological structure. Okay? Before we talk about screw dislocations, we have to review. This looks like it has no charge. Right? It's true that there's extra layers disappearing, but then on the other side, this happens. This is like you built a building and there's no connection on these floors, but they're connected on the top and the bottom floors. And you say, oh, there are the 2 disclinations, 2 plus a half disclinations. So the charge should be +1. Of course, it's not, because there's the minima, and on the minima, there are the negative charge ones. So see, this has no disclination charge. There's no problem with the layer normal globally, and there's no problem with which layer you're on globally. Yeah, there's some bad stuff in here, but who cares? Right? Far away, there's no problem. You can't detect this by doing some pathway out here. Okay, and here's actual real pictures. These things are called oily streaks. They actually appear in liquid crystals, and you can just see them. Let me draw another picture of 2 plus 1/2 disclination. So here's one where I draw it in 2 dimensions. Here are the layers. Here are the 2 extra layers built in. And you can see that there's no dislocation. There's no problem with what layer you're on. But, oops. But if you go far away and you calculate the layer normal will rotate around by 2 pi. But you can tell which one you're on. This one, this one, this one, this one. You can label them. Okay? So this has a net holonomy of the layer normal, but there's no problem with which layer you're on. How can you make a screw dislocation? Can you make a screw dislocation the same way I described, where you make it out of disclinations? Yes. Okay? And the way you do it is you take this and you twist it. Okay? So you twist it. And these lines sweep out a helicoid. Out at infinity, there's a helicoid being swept out. But on the inside, it's not a helicoid. On the inside, there's no place where there's a phase singularity. Right? You don't know which way the normal points, but there's no phase singularity. Here are the 2 disclinations. They're wrapping around in a helix, a double helix as they go around, and they sweep out a dislocation far away. But inside, there's no problem. There's no place where they have to melt the crystal. Okay? Where'd the charge go? Anybody? The charge disappeared because you see at the center of a helicoid, right? If you look at the director or the layer normal at the center of a helicoid, and imagine filling this space with other helicoids, so you can fill it in. There, the layer normal lies in the xy plane and it rotates around by 2 pi, and there's a disclination. But then these things, some people say escape into the third dimension. I'll say escape from the second dimension. Okay, they come out and they rotate eventually far away. The holonomy of the layer normal goes to 0. It gets smaller and smaller. It rotates on a tighter and tighter cone. So if you try to measure the holonomy far away, it's gone. So where'd it go? I mean, it looks like it's disappeared. But let me show you where it went. Okay, so Sir Charles Frank, right? This is in some paper he wrote in 1958, the most ever cited paper on liquid crystals ever, one of the best papers ever on liquid crystals. No, the best paper, at least by citation index, at least by the way that grant monitors and tenure committees would view it, right? He would definitely get tenure and get a grant, okay? He talks about saddle splay. And he writes down this term, and ignore the sign. I'm choosing my convention, right? The saddle splay is a total derivative. It measures how n would move if it were normal to a surface. Does it have the structure of a saddle? It measures the saddleness, okay? N's a unit vector that's normal to the surface, that tells you which way the liquid crystal points. This is the saddle splay term, but see, it's a total derivative. So it's no Lagrangian. It doesn't change anything. It only changes things at boundaries, right? But I just showed you boundaries. The defects are boundaries. They're places where there's a hole in the sample. So where the defects are, there are boundaries, and you actually get something from the saddle splay, right? Aficionados of the blue phase know that this is the whole basis for stabilizing the blue phase. So let me calculate this vector for you. The one that I take the divergence, of which I take the divergence. First of all, I can write this in terms of the length integral, if it's homogeneous along the length of the defect. And then there's LZ, and then I turn it into a Stokes theorem or something, and I integrate around the circle. Nu is the layer normal, and I integrate this at infinity and R naught. Okay? Well, if I take this planar texture n, like so, and I guess there should be an R here, sorry, right? And I calculate this vector. So this vector, clearly when I look at n, and I look at the winding of its orientation, it rotates around by 2 pi m. But I also notice that this vector goes like minus m over r. If I took this vector and integrated on the inner surface, I also get minus 2 pi m. Right? So this vector and this vector both have this winding by 2 pi m. But when I try to measure the winding or the holonomy of this vector of the actual director, I get 0 far away. But I don't get 0 far away when I measure this one. In a screw dislocation, what's going on? There's Gaussian curvature. Okay, and the Gaussian curvature is what is erasing the disclination charge, but it's actually measuring this other charge, the saddle splay. I didn't tell you this, but in fact, you can take this integral and turn it back into an integral where you integrate over layers. A is the spacing between the layers, and this is the integrated Gaussian curvature over the layer. It's an invariant of the helicoid. Since the helicoid has some net Gaussian curvature per unit length, you actually pick up the integrated Gaussian curvature. The saddle splay knows that the lines going around, the normal going around by 2 pi in the center of a helicoid predicts the Gaussian curvature of the whole thing because it eventually goes to flat layers. So eventually, this vector is 0 when it rotates out of the plane. right? But that's okay, right? This goes to 0 at infinity. It's the defect in the center that tells you and predicts all the Gaussian curvature that sits on the helicoid, which is out there. I don't know what this funny curve is, sorry. Okay? How do you connect screws to edges? I showed you that picture where there were screw defects, edge defects on top, and they were twisting around. You see, here you have a screw defect. Here's this half disclination. Here's the other one, the red one and the blue one. The blue ones are going around in a helicoid. The red ones are too, until they get to this layer. So you can imagine it going through here. It comes out here. And then it connects to this -1/2 defect. And then it turns into an edge defect. And the layers up here, there's no problem. There's no tear. On this side of the board, where you guys are, you just fill it in with layers, right? And there's a distortion in the layers, but that's okay. You have now continuous layers everywhere. So what happens is the screw turns into an edge. Okay. It's a place where you have a situation where in one case you had a +1/2 winding. In the other case, you had a -1/2 winding. Now, of course, if this were merely a vector field, or not a vector field, a line field, you could continuously go from this to this, right? By rotating the molecules out of the plane. But that would require the molecules to twist. And layers can't twist. So in a smectic, it's impossible to go smoothly from here to here. I just showed you that because I just calculated that invariant, the integral of that vector around the center. It tells you how many things you hit, right? So there must be a new kind of singular point where a -1/2 becomes a +1/2. You know what that means? That means screw defects and edge defects are different. Even though the dislocation charge, and you integrate d phi around a closed loop, gives you the same answer, you can tell the difference. There's a point where something happens, right? And so I'll leave you with that. Here's the screw, which has two +1/2 disclinations wrapping around. They are wrapping around and tilted in such a way so that there's still no net disclination charge at infinity. It's all shrouded in the Gaussian curvature, which turns out to be the right invariant to the correct invariant to calculate. These don't have any Gaussian curvature. They're flat as flat can be, right? Because they have a -1/2 and a +1/2. They add to 0. And so here you have the edge, and here you have the screw, and you could connect them, but there's this new point, and you can tell the difference between a screw and an edge. And that is because there's a density wave. And the density wave gives you extra information. It's also because we get these materials get to enjoy this extra Z2 symmetry, that you can break them apart this way. Okay, so I'll end. I'm telling you there's this new topological charge that actually distinguishes topological, global. It's some global charge because you have to integrate it over the whole surface that distinguishes edge from screw dislocations. The topology of the ground state manifold is what constrains where the defects sit. Now, somebody said to me, you know, when I read books and they talk about dislocation lines, they drew curvy dislocation lines, right? They don't draw them always as screw edge. They, you know, they're arbitrary loops. You know, you can have an arbitrary loop if you're willing to melt the crystal. And it's possible energetically that it's just better to melt the crystal and have a big old hole in your crystal than it is to actually put everything on the disclinations. And certainly when we think about how crystals melt in terms of dislocation loops going everywhere and messing up the layering, that's fine. When they melt, the energy cost of melting the crystal is small near melting. That's the whole point. Deep in the crystal phase, however, you would expect, or one would expect, that I would expect that delta rho likes to not be 0, and it forces the disclinations to sit on those special places. And then you have this distinction, clear distinction between screw and edge. When you can resolve the disclinations, you can resolve the structure of the defect. Dislocations are made. Moving a dislocation requires melting. And then here's this question to which I don't know the answer. Michael Berry said to me, someone must know the answer. I said, well, maybe someone once knew the answer. but I don't know what to ask now. What are the extra constraints? Now, if I imagine trying to move a dislocation through another dislocation, which can happen, how do they interact? How do they go through each other? Is there some other invariant? Do I have to worry about how these disclinations pass through each other? If you look in the literature, what are they called? Zigs and zags, jogs and jags. There's stuff written, you know, by Nye, by Eshelby, by Hirth and Lotha, you know, by Nabarro, all on this stuff with names for what happens. But they always draw pictures of specific crystals having specific deformations, right? So there's something missing that I don't know. I should again remind you that this work was done, some of this work was done with Helen and Tom and Brooke. Some of the work on the new kind of charge was done with Hillel. And I have this new student, Paul, who is working on this latest thing about how to measure and consider how screw defects have a different topology. And of course, we were funded by people. Okay, thank you.